Hey guys, Mr. Wood from Mrs. Wood's office where she does her work. And I just want to do a short lesson today, not a very long lesson, kind of get through chapter, kind of something that we would have typically went over in first year chem that because of the virus last year, we wouldn't have got to. So at least give it to you, and then I'll come back and review this on Monday. And probably, I don't think we're going to get to test on 12 and 13 till after spring break. So that is okay. We're just going to do the best we can. Okay, here's jokes. Jokes today, like I've shared with you, are from my t-shirts. Maybe I'm repeating myself, but this is something I'm hoping we'll need to start talking about. I always have my students create their t-shirts. And this was from 2019. So this was the front. Here's the joke. So you can see a 1 molar solution. I might be repeating myself. You might have seen this one. But here is another one, AP Chemistry 2 potassium 19. Of course, so that means that's 2K19. This is class of 2019. And it says, he, laughing gas. Good chemistry humor. Here's another year. One lab we really need to do in April is a titration. And you guys, again, that had chemistry last year, you would not have done that. And it's important that you do that. We did a redox titration back in the fall in September, but we need to do an acid base one. But anyways, it says drop the base. And you guys will know what that means when we do this lab in the pink phenolphthalein color. And then I think I've showed you this on the back. I try to do chemistry jokes, but there is no reaction. So, okay, so those are the jokes. So here we go. And again, not a very long lesson at all. So you just hang in there. And then I heard somewhere that I think on the average, a person needs to hear something 7 times. And after 7 times, then they remember it. Of course, for Mr. Wood, I need to hear it about 50 times before I remember it. But anyways, we'll try a couple times here. Today, hopefully you're following along. Again, I'll make this really short, but back to the notes. Okay, so what we were, and actually where we were was right here. Okay, so here are the notes, and this is the notes that I had up, and there's really 2 key things I want to go over here. But when molecules collide, or the rate of reaction is usually dependent upon the temperature. Therefore, the rate constant increases with temperature. So if you look at what's being graphed here, on the y-axis is K, the rate constant, and on the horizontal axis is temperature. And you can see that as temperature goes up, the rate constant goes up. And when molecules collide, part of their kinetic energy is transformed into vibrational energy, which, if enough, will rattle a molecule apart by breaking its bonds. So back to to here. So this is something I've actually written down before, but I want to do this again, and I'll put this on the 12-13 test. But the rate of the reaction depends on, again, so you should note this, okay, rate depends on, number 1, the temperature, and number 2, on concentration. And if you think about rate is equal to K, the rate constant, times the concentration of the reactants to whatever order they are. Well, so if concentration goes up, the rate will go up. If concentration goes down, the rate will go down. And again, I've already talked about this, but I'm just making a point. So you get this. You'll see this on the next test. So the rate constant depends on, so we're talking about K, the lowercase k. It also depends on temperature. That's what that graph just showed. And it also depends on a catalyst. And that's something we're going to talk about next week, a catalyst, and what a catalyst is and how a catalyst is involved in these reactions. So, okay, so back then to the notes. And again, I don't want to spend very much time on these notes. Let me do this. Okay. messed up. Mr. Wood always messes up. But okay, so back to the notes. Okay, so this is where we were. And then the next thing that I want to just introduce, and this again is something we would have talked about in first year chem, is this, which is called an activation energy diagram. And I want to talk about this just quickly today, and I'm going to come back on Monday and talk about it again. But this, if we look at what it says at the top, colliding molecules must have a minimum amount of Ke, kinetic energy, or activation energy, which is abbreviated EA, in order to react. And so just to review what you should know, okay, so for a reaction to occur, number one, molecules have to collide, the collision theory. So molecules have to collide, number one. Number two, they have to have this minimum energy, this activation energy. And number three, they also have to be oriented correctly. Okay, and this is something we talk about in AP Chem. So they have to collide, number one, the molecules do. Number two, they have to have this minimum amount of energy. And number three, they have to be oriented correctly. Okay, so now kind of a little bit more on this diagram. So I'm going to talk about this for a second. So the activation energy diagram for this reaction. So I'm going to write some stuff on the board. And this is, again, something that we would have spent some time on in a day or two in first year chem. And so this is something that would have been review, but because you guys didn't have this in first year chem, then it's important that we spend a little bit more time on this. So you can see this diagram. And again, I'm going to come back to this on Monday, but okay, so this is the way it looks. And I want to identify the key parts on an activation energy diagram. Okay, so here's the key parts and this is called an activation energy diagram. Okay, that's what this is called, an activation energy diagram. Remember, activation energy is the minimum amount of energy to get a reaction to occur. So what we've got is we've got energy on this axis, and we've got time on this axis. Okay, so I'm going to use my green marker to kind of identify the key spots. Okay, so the graph looks like this, the one that's in the notes. And so the key parts to the graph, the first thing that's key is what's right here. And these are the reactants. Okay, so this is where the reaction starts. The reactants, that's what we start with, is the reactants. So that's first thing. The second thing, which makes sense, is the products, if that's where we end, the products. Okay, what this is kind of like, this is showing the energy barrier in a reaction. And it's kind of like if you like to go to Mary Jane or Winter Park to do your snowboarding or skiing. It's kind of like going over a mountain pass is what it is kind of like. Let me light that. Light is kind of glare off there. Okay, the third key point is the very top of this, and it's called the activated complex. Okay, and this is the top, and this is where when you get to that energy amount, now the reaction could go back down to the reactants, or it could go on to the products. Okay, so the reactants are where we start, the products are where we end, and then the activated complex is at top. Now, probably the key things on this graph is the difference between the start and the beginning. And this is the EA. This is the activation energy. And so it logically makes sense that the bigger or the smaller, the bigger the activation energy is, the slower the reaction is going to go. The bigger this is, the slower it's going to go. There's a bigger energy barrier. And I'm having a hard time with the glare of that light. And then, I don't know if you can see it better or not there. But the smaller that is, then the faster it's going to go. And I'm going to show you a YouTube video of this real reactive stuff called nitrogen triiodide. Okay, so we start with the reactants. We end with the products. The top is the activated complex. The difference from the top and the beginning is the EA, which is the activation energy. That is the energy barrier. And the last thing is the difference between the ending and the beginning. So this in here, and this is delta H. And this goes way back to chapter 6. Delta H, remember, is products minus the reactants. Okay, back in chapter 6. Well, here, if I do the products minus the reactants, it's going to be negative. And so delta H, if you remember, when delta H is negative, it's exothermic. So this graph is showing an exothermic reaction. If I have a graph that looks like this, so the delta H here, so again, delta H is the difference between these two. So products minus reactants. In this case, the delta H would be positive, so it'd be endothermic. Okay. And I'm going to, again, I just wanted to introduce this. Another thing, and I'm going to come back and talk about this Monday. So hopefully you spent the 10 or 12 minutes watching this. I did have good jokes for you, but the reverse reaction would be starting here and going this way. So the activation energy for the reverse reaction would be the difference from the top and the products because we're going backwards. And the delta H would be the same number. It would just be a different sign. So, okay, I'm going to stop there. I told you I was not going to take very much time, and that's hopefully what I did. And hopefully you'll watch this, and we will get back to work on Monday. Have a good weekend, guys. And I'm still going to make the quiz and the lab due on Wednesday. I'm not going to change that. I'll give you some time to kind of finish those up in class on Monday, Tuesday. Have a good weekend, guys. Bye.